Let's take a look at the last of the indeterminate forms. And you may hear a little noise in the background. My wife is doing laundry. But in this indeterminate form, these are the exponential indeterminate forms, and there's three of them. There's 1 to the infinity, infinity to the 0, or 0 to the 0. And let's take a look. The thing is, actually, some of them you can imagine with 1 to the infinity where you might have some issues with infinity to the 0. These infinities may cause issues, but 0 to 0 seems pretty innocuous. And in fact, in algebra classes, you probably said anything to the 0 is 1, and so sort of assume that something like that would be 1. But we'll see, it's not always. All right, and then the thing is, though, let me remind you again that you cannot apply L'Hopital's rule to anything unless it's approaching 0 over 0 indeterminate form or infinity over infinity. That is the only things that L'Hopital's rule applies to. Now let's take a look at this. All right, and why these are indeterminate forms. Okay, the others we might be able to see a little more clearly why they're indeterminate forms. These perhaps not so much. This is the graph of y is equal to the natural log of x. And so what we're going to do is we're going to consider the natural log of each of these expressions. Now, I should really put quotes around these. Perhaps I will here. These are not really equations, all right? We can't, I mean, some of the stuff we're doing, I don't have an infinity. I can't put an infinity into an expression and evaluate it, so I can't really say these are equal. But look at the ID. We have something that's approaching 1 and something that's approaching infinity. And if I think about the natural log of that, well, this thing that's approaching infinity is an exponent, so it can come out in front. So I'd have something approaching infinity times the natural log of something that's approaching 1. And notice if we approach 1, the natural log approaches 0. So this would be something approaching infinity. Again, maybe I better put quotes here. All right, times 0. Okay? That's what would happen to the natural log as that expression approached 1. So that's, of course, an infinity times 0 indeterminate form. All right, in the next one, we'd have something approaching infinity raised to something that's approaching 0. Again, we can do the same sort of thing, and I think you can see what's going to happen here. We'll have something that's approaching 0 out in front times the natural log of something that's getting big, that's approaching infinity. And if something approaches infinity, notice its natural log gets bigger and bigger and bigger. Its natural log approaches infinity. So this would be, again, a 0 times infinity indeterminate form. Well, now how about this last one? So we have something approaching 0, and its power, the power on it is also approaching 0. The base is approaching 0, and the exponent is approaching 0. So again, if I take the exponent out in front, all right, I'll have something approaching 0 out in front times the natural log of something that's approaching 0. And of course, as something approaches 0, what happens to the natural log? The natural log goes to negative infinity. So this would be 0 times, well, negative infinity, but it didn't really matter whether it was negative infinity or positive infinity. All right, so they're all approaching that infinity, 0 times infinity indeterminate form. Now we should keep in mind what we've done here. We've looked at the natural logs of each of these. You know, we've used natural log to determine that they are approaching indeterminate form, and then always the indeterminate forms will be a 0 times infinity. That's the way that you solve these problems. You look at their natural logs, and you'll get something that's approaching an infinity times 0 indeterminate form, and then you apply, you treat that as we did before, and apply L'Hopital's rule if need be. Let's take a look at an example. All right. Let's take the limit as x approaches positive infinity of 1 plus x, so the base is approaching infinity. The exponent is approaching 0, so notice this is an infinity to the 0 indeterminate form. Okay. Well, now here's what we could do with this is what we'll do is we'll take the natural log of this. All right. Now notice these are not equal. I've divided this into two columns because they're not the same. All right. So we'll take the natural log of this expression. Okay, just like we used natural logs to see that these were indeterminate forms. Now, because of this that the natural log is continuous, I can take the limit out, and I'll have the limit as x approaches positive infinity of the natural log of 1 plus x raised to the 1 over x. All right, and now we have this natural log of something raised to a power, so I can apply the properties of natural logs. I can take that exponent out in front. This will be the limit as x approaches positive infinity of 1 over x times the natural log of 1 plus x. And of course, that could be written as the limit as x approaches positive infinity of the natural log of 1 plus x over x. And now let's take a look. As x approaches infinity, 1 plus x approaches infinity, so its natural log will also, and x approaches infinity. We can apply L'Hopital's rule, all right, because we're approaching an infinity over infinity indeterminate form. So what does L'Hopital's rule say? It says we have the same limit as x approaches positive infinity of, well, when I take the derivative of the numerator, I'll get 1 over 1 plus x. I have to use the chain rule times the derivative of the inside function, which is 1. Okay, so I have 1 over 1 plus x times 1. The derivative of the denominator is 1, so I'll have this limit. And of course, this is just the limit as x approaches positive infinity of 1 plus x. And that limit is, of course, 0. That limit is 0. Now we have to be careful. We're not at the end of the story yet, because you see we have taken this is the natural log. All right, this is the natural log of the limit we want to take. To undo the natural log, we have to take and apply this as an exponent on e. Remember, e to the x is equal to the natural log of the e to the x is the inverse of the natural log of x. So I took the natural log here. I'll have to apply the inverse function to undo it at the end, and what we'll get is e to the 0 or 1. So this limit as x approaches infinity of 1 plus x to the 1 over x is equal to 1. Okay?